Hi everyone, let's continue. The next topic is proof by cases. Proof by cases is used when the original hypothesis naturally divided itself into various cases. Here is an example. Prove that 2m squared plus 3n squared equals 40 has no solution in positive integers. That is, 2m squared plus 3n squared equals 40 is false for all positive integers m and n. So here, let's show it. So we can suppose that 2m squared plus 3n squared equals to 40. Okay, and here m and n are positive integers. Let's try to solve this equation, and if we cannot find the solutions, then we can say no solutions. Okay, so now because 2m squared is greater or equal to 0 and the 3n squared is greater or equal to 0, so we get some restrictions. So if we require 2m squared is greater or equal to 0 and it must be less than or equal to 40, because the 3n squared is greater or equal to 0, then the 2m squared is less than or equal to 40. And also we have the 3n squared is bounded between 0 and 40 as well. Okay, so let's look at the m and n. Okay, so since m is a positive integer, okay, then we know it's greater than 0, but okay, look at this guy. 2m squared is less than or equal to 40. It looks like m squared is less than or equal to 20. And then m is like less than or equal to square root of 20. Square root of 20, then think about a 4. A 4 squared is 16, okay? And then 5 squared is 25. But 5 squared 25 is not less than or equal to 20. So that's why m is at most 4. So far so good, everybody, because 2 times 5 squared is 2 times 25 is 50. That is bigger than 40, so we cannot take the 5. And also, since n is positive integer, similarly here, we get like n squared is less than or equal to 40 over 3. Okay. And we know n is a positive, so it's greater than 0. And how big can it be? If we pick 4 squared is 16, but 3 times 16 is 48. So 4 does not work. Let's choose 3. 3 squared is 20. 3 squared is 9. 9 times 3, 27. 27 is less than or equal to 40. So we have n is less than or equal to 3. Okay, and here we can see 3 times 4 squared is 48, which is greater than 40, so we don't pick 4. Okay. So that means m can be 1, 2, 3, 4, and n could be 1, 2, 3. Okay, so let's separate the cases. Okay, so we're gonna check the following cases. Okay, so we're gonna have m and n. So let this be n. N is 1, 2, 3. And let this be m. M is 1, 2, 3, 4. Okay, now let's see. And we want to have 2m squared plus 3n squared. We want to see whether that equals 40. Okay, now let's see. 2m squared, so here is 2, 1 squared is 1, plus 3, 1 squared is 1, equals 2 plus 3, that's 5, not 40. Next, 2m squared, 2 squared is 4, 3 times 1, 2 times 4 is 8, 8 plus 3, 11. Next, 2m squared, 3 squared is 9, plus 3 times 1. Okay, 2 times 9, 18, 18 plus 3, 21. And then here we have 2m squared, 4 squared is 16, plus 3 times 1. 2 times 16, 32, 32 plus 3, 35. So far, so good, everybody. So when you do your homework, I strongly recommend you to do not use your calculator, because sometimes when you calculate by hand, maybe at the beginning, it might take you more time to calculate, but eventually you can build a sense with the numbers. Okay, next, 2m squared, so 2 times 1, 3n squared, 2 squared is 4. 3 times 4, 12. 12 plus 2 is 14. Next, 2m squared, so 2 times 4 plus 3 times 4. Well, 2 times 4, 8. 8 plus 12 is 20. And then 2 times 9, 3 times 4. So 18 plus 12, 30. And then this is 2 times 16, 3 times 4, 32 plus 12, 44. So far, so good, everybody. Okay, this is 2 times 1, 3 times 3 squared is 9. 27 plus 2, 29. 2 times 4, 3 times 9, 27 plus 8, 35. And then 2 times 9, 3 times 9, right? Okay, so 18 plus 27 is 45. 2 times 16, 3 times 9 is 32 plus 27, 59. Okay, so here are all the cases. And we can see none of them equals 40. So that's why we can conclude that 2m squared plus 3n squared equals to 40 is false for all positive integers m and n. So we don't have a solution in this case. So far, so good, everybody. Yeah, so you can see we separate into cases, and actually there are 4 times 3, 12 cases in this case. Okay, let's continue to the next example. Prove that for every number x, x less than or equal to absolute value of x. Okay. Let's recall what is absolute value of x. Well, absolute value of x equals x if x is greater or equals 0, and it's minus x if x is less than 0. Why is that? Okay, just give you an example. Negative 2, absolute value is 2. But what is 2? 2 is actually negative 2 of 2, because negative 2 is negative, so when you put a negative sign in front of it, it actually makes it positive. So that's why here, x is negative, then minus x is positive. And keep in mind, the absolute value is always positive. And of course, absolute value of 2 is 2. Okay? So, how do we show it? We want to break the absolute value, so we separate into cases. So, here are the cases. First, if x is greater or equals 0. Well, in this case, absolute value of x equals x. So because it's equals x, we know it's also equal, greater equal than x. So now we know the proposition x less than equal to absolute value of x is true. Okay, second, if x is negative, then absolute value of x is is just negative x. But negative x is actually positive, right? And x is actually negative. So we have absolute value of x is greater than x. So that's the same as x less than equal to absolute value of x. Okay? Because less than or equal is or. So if it's less than, of course it's less than or equal. Okay, so we say in both cases, we get x less than absolute value of x. And that's finished the proof. Okay? Alright, let's continue. Next topic is proofs of equivalence. So some theorems are of the form P if and only if Q. Such theorems are proved using the equivalence. So you prove P implies Q and you prove Q implies P. Okay? So i.e. to prove if and only if, you prove if P then Q and if Q then P. Okay, so here are some examples. The first one, we prove that for every integer n is odd if and only if n minus 1 is even. Okay, so we have two directions. Let's prove this direction. Well, this direction, what does that mean? We want to show that if n is odd, then n minus 1 is even. Okay, so suppose n is odd. What does that mean by definition of odd? N equals 2k plus 1 for some integer k. Right? Then what is n minus 1? Well, that's 2k plus 1, then minus 1. Well, the 1 cancels, so we get 2k. Well, because k is an integer, so this guy is even. So now we have shown that n minus 1 is even. On the other side, we want to show that if n minus 1 is even, then n is odd. Okay, so we suppose n minus 1 is even. Then by definition of even numbers, n minus 1 equals 2k for some integer k. Or you can say, suppose n minus 1 is even, there exists some integer k such that n minus 1 equals 2k. It's the same thing. So I find this way short, so that's why I put this way. Okay, and then n is an n minus 1 at 1, so that is 2k plus 1, because k is an integer, so that's why this guy is odd. Therefore, both of them, we get, combine them, we get if and only if. Okay? Let's continue. So here I don't have enough space, but if you have more space here, you should say therefore n is odd if and only if n minus 1 is even. It's good to write down the whole sentence down here. But I ran out of space, so I just put this guy here. Oops. Okay, let's continue. Okay, so this example, let A, B, C be set. Prove that the following are equivalent. So what we had in our last example, we only have two propositions and we want to show their equivalence. But here we have three propositions. How do we show their equivalence? So one way is, so you have A, you have B, you have C. Oops. So one way to show that they're equivalent is you can show 1 implies B, and B implies C, and C implies A. Then they're all equivalent. Okay, so let's follow this order. So we're gonna show 1A. The first is A implies B. Okay. So suppose A is true, so assume A is a subset of B. Okay, so there's something wrong with my word. Let me fix it. We want to show A intercept B equals A. So in order to show A intercept B equals A, so which means we want to show A intercept B is a subset of A, and we also want to show A is a subset of A intercept B. Okay, so this direction first. So suppose X is in A intercept B. Oh, then by definition of intersection, okay, so because A intercept B is a subset of A, then we know that X is in A. Okay, if X is in A and B, then X is in A and X is in B. Okay, so this direction is easy. How about the other direction? So suppose X is in A. Okay, we want to show X is in A and intercept B. Okay, but here, since A is a subset of B, by definition of subset, we have X is in B. Okay, and since now we have X in A and X in B, then we get X's in A and B. Okay, so therefore combine those two directions, we get, so we say hence A intercept B equals A. So now we have proof B, okay? And next we want to show B can imply C. So we assume that A intercept B equals A, and we want to show that A union B is B. Okay, so now let's see. So it's equal, so it also contains left-hand side is subset of right-hand side, and the right-hand side is subset of left-hand side. So let's look at the first direction. Suppose X is in A union B. Okay, then we have X is either in A or in B, right? Or both. Actually, but this or already considered the case in both of them. Okay, so that's why we have two cases. It's either in A or in B. So case 1, if X is in A, what happened? Okay, so first case, if X is in A, then because A intercept B is A, so X is in A intercept B. Oh, that means X is in B, right? X in the intersection, it means X is in A and in B. Okay, so we get that. But for the second case, oh, we have X in B for the second case. So that's why combine the both cases, we get x in B. And that's what we want, right? We want to start with x in A union B, and we want to show x is in B. Then so we get A union B is a subset of B. Okay, let's continue. The other direction, we suppose x in B. Wow, because B is a subset of A union B. This is obvious, right? By the definitions of union. So that's why we have x is in A union B. So this is just by definition of union. So far, so good. That's why, hence, we get A union B equals B. Okay, next, we have the last one. So last one, we want to have C implies B. Let me see, do I have enough space here? Okay, so C implies A. So A union B is B, and we want to show A is a subset of B. Okay, so assume that A union B is B. We want to show that A is a subset of B. Okay, so suppose X is in A. All right. Since that A is a subset of A union B, but A union B is B, then we know A is a subset of B, so X is in B. Okay? And therefore, we have A is a subset of B. So now we, this one is, oops, okay, this one is actually C implies A, not C implies B. I put it wrong. Okay, so now we have shown that, so we can say, does A subset B. So now we have shown A implies B, B implies C, and C implies A. Therefore, those A, B, C are equivalent. Okay? That's finished the proof. Okay, so and this is the proof when we have more than 2 propositions and we want to show their equivalent. Let's say if we have 5 propositions, then we just wrap a circle, right? 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 1. So we wrap a circle and then we can show they are all equivalent. So far, so good, everybody. Okay. Next one, existence proof. Okay, so a proof for there exists X, P of X, is called an existence proof. So in section 1.5, we showed that one way to prove it, to exhibit one member A in the domain of disclosure that makes P of A true. So we just need to find an example to show it works. Okay, so let's look at this example. Let A and B be real numbers with A less than B. Prove that there exists a real number X satisfying A less than X less than B. Well, real numbers, we have A here, we have B here. Can you find a number in between? I would naturally, so by the way, this X depends on A and B. So I would say X, the expression or formula of X must be a function of A and B. It depends on A and B. So can you find any numbers between A and B? Well, this looks like the midpoint of them, right? The midpoint formula is a plus b over 2. So yes. Yes, see, we have find x, which is a plus b over 2. Then we have x is greater than a and less than b. And then this finish. Okay? So keep in mind here, a and b are any real numbers. So here a and b are arbitrary numbers. Okay, so you cannot just pick 1 and 2. So you should let a and b be arbitrary. Okay, and then the x is in terms of a and b. It should depend on a and b. Okay, in this case, x is a plus b over 2. All right, let's look at the next example. Prove that there exists a prime number p such that 2 to the p minus 1 is composite, which is not prime. All right, so we find the example by trial and error. Okay, so by trial and error. Let's go down the list. Okay, so first of all, p is a prime. So what are the prime numbers? Well, the prime numbers is 2, 3, 5, 7, 9 is not, 11, 13, 15 is not, 17, etc. Okay, let's see whether those are the enough one. Okay, we want to figure out 2 to the p minus 1. So this guy, 2 to the 2 minus 1, 4 minus 1 is 3, is prime. So we want to find a number which is not prime, right? So here 2 to the 3 minus 1, 8 minus 1, 7. 7 is prime, so not this one. 2 to the 5th minus 1, to the 5th, 32, 32 minus 1, 31. 31 is prime. Okay, so let's continue. 2 to the 7 minus 1. Well, 2 to the 7 is if I hope you can like remember the 2 powers. 2 to the 1 is 2, to the 2nd is 4, 2 to the cube is 8, 2 to the 4th, 16, 2 to the 5th, 32, 2 to the 6th, 64, 2 to the 7th, 128. So 128 minus 1 is 127. And to figure out 127 is prime, you can try to find the divisor of this, and then you realize this is actually a prime number. Okay, and 2 to the 11 minus 1. Oh, you know 2 to the 10 is 1024. I see this number a couple times. Yeah, 2 to the 10 is 1024. So 2 to the 11 is 2048. 2048 minus 1 is 2047. Is this guy a prime or not? Actually, this guy is not a prime. It's a composite. So it equals 23 times 89. Well, you might ask, well, how can I come up with this number? Well, you either need to try a lot of prime divisors and see whether they work, and it takes a long time to figure out this decompositions. Think about the list of prime numbers: 13, 17, 19, 21 is not, 23. So you go down this list. So you use this number and divide it by these guys and see whether you can get the remainder is 0, okay, or you don't get a decimal when you divide it using your calculator, and then I come up with 23. When I divide by 23, I get 89. So it's not a decimal. So we know that's a the 2047 is a composite. Okay. And now we have find a prime number such that 2 to the p minus 1 is composite. So now we have find this example. That example is 11. And this guy is not a composite. So now we have finished. Okay, so we already find number 11 and it works. Okay, so this is the existential proof. And for this guy, you just need to find an example. Okay, so that's it for session 2.2. We will continue in the next class for session 2.3. Have a nice day. Bye.